All right, here we go with the Chapter 5 Homework B review. This homework assignment has been open for a while since it started before the spring break, which got extended, and now here we are. So it feels like it's been about 2 weeks since we've done anything related to this course. It feels more like 2 years for most of us, I'm sure, but we're back at it and the show must go on. All right, so the average this week was, or this assignment was 9.34 out of 12, almost identical to last year, so right in line with what we typically do. This assignment did have a lot of sort of numerical questions, as you'll see as we go through them. Some of those had lower success rates, perhaps just because there are a lot of calculations involved, and even just missing one step can be enough to cause it to be missed. So we'll go through all of these, and basically what I have here is just representative examples of the different problem types that we would have encountered as we go through this assignment. So this is all about stoichiometry, so every problem we're going to do is related to stoichiometry in some sense. All right, so getting into it, we can go to the first problem here. So what we're going to do is we're going to go through a bunch of different types of stoichiometry problem, and it is possible in these to classify them as sort of different problem types. Now, it's not necessarily important that you do that before you start, but we're going to see here that there's several different variations on stoichiometry problems, and if we sort of classify them in different ways, we can see what are the steps that are required to solve these. So what's often helpful to do, and I would always recommend you do this in one of these problems, is there's a lot of words in the problem, a lot of information in many cases. But first we're going to focus on the end and sort of look at what it's asking us. So before we get into all the details, what we see is we have 5 moles of NH3 reacting stoichiometrically with how many moles of O2 to form how many moles of NO. So everything we're dealing with here is moles. Moles of NH3, which is one of the reactants. We're trying to find moles of O2, which is the other reactant, and then forming moles of NO, which is one of our products. So this is what we would classify as a mole-to-mole stoichiometry problem. And again, it's not necessarily important that we classify it before we start. But if we know that it's mole-to-mole, we can think about the steps that we need. And in addition, we can now go through the rest of this. So the first step in the Oswald process for making nitric acid, here's our balanced equation. We don't have to worry about balancing it. And now we're ready to start the problem. So this is a 2-part problem. So the first thing we're looking for is moles of O2. So we always write out what we're looking for, and then we're going to start with what they give us. So we're reacting 5 moles of NH3, and we're trying to figure out how many moles of O2 react with that. So we have 5 moles of NH3, and in stoichiometry problems, the first thing you typically want to do is convert to moles. We don't have to do any conversion here, and so we're ready now to just use the mole ratios directly. So in a mole-to-mole stoichiometry problem where you have moles of one substance and you're calculating moles of another, it's typically only going to be one step. You just have to find you use the mole ratios from the balanced equation. Okay, so if we do this then with 5 moles of NH3, trying to find out how many moles of O2 we have, we'll put moles of O2 in the numerator and moles of NH3 in the denominator so that it cancels, and we just need the balanced coefficients, which are going to give us the ratio of those moles. So in the balanced equation, we have a coefficient of 5 in front of O2, and then we have a coefficient of 4 in front of NH3. And so when we multiply this across, we'll notice that all our answers are in fractional form, so we're going to just leave it as a fraction. 5 times 5 divided by 4, which is 25 over 4. Moles of O2. The only answer that even has that is E, so if we trust ourselves to do the first part right, we don't even have to do the second part. Let's verify that the second answer would be 5. So we're trying to figure out how many moles of NO form. So if we're looking for moles of NO, it's going to really be the same process, just making sure we use the correct mole ratios. So we still have 5 moles of NH3 as our starting point. That's how much we're reacting. And then to figure out how many moles of NO forms, we're going to look at its mole ratio, moles of NO over moles of NH3, such that moles of NH3 cancel, which I didn't explicitly show last time. And we see the coefficient for NO is 4, the coefficient for NH3 is also 4, so 5 times 4 over 4 is just 5 moles of NH3. And so that would be the second part of our answer, which is correct also. So this was a mole-to-mole stoichiometry problem, and in this case, you don't have to do a bunch of different steps. It's just one step to convert moles of one substance into moles of another using the mole ratio. That is sort of the key concept of stoichiometry. But then there are also many other variations on these because we don't often have moles of reactants and products, or sometimes we're asked for a different quantity as our answer. So in this case, we have the ethyl alcohol and gasohol. Ethyl alcohol, ethanol is an additive found in gasoline, usually about 10% if you look at the gas pumps today. And so the ethyl alcohol and gasohol burns to form CO2 and H2O. That's a typical combustion reaction. If the combustion reaction consumes 8.04 moles of C5HW, which is ethyl alcohol, reacting with excess O2, how many grams of water are formed? So again, if we want to classify this as a sort of different problem type, here we're given moles of one chemical substance and we're asked for grams. So this would be called a mole to mass type problem if we want to sort of put it in a category where we're starting with moles of one substance and calculating mass of another. So as we'll see, this is just going to add one step for us. But whether we categorize it or not, we just again have to think about what are we looking for and what's our starting point. Now in this problem, we didn't give you the chemical equation directly. So anytime you're doing a stoichiometry problem, you have to have a balanced chemical equation. And so we need to go through and write that out. So we're doing a combustion reaction, which is going to be some substance, usually a hydrocarbon or something with oxygen in it as well, reacting with excess O2, and the two products are always going to be CO2 and water for combustion. So this is our combustion reaction, C2H5OH plus O2 is the other reactant in a combustion, and then the products in a combustion equation are always going to be CO2 and water. In this particular problem, the important thing that we need is the ratio of C2H5OH to water, because those are the two substances we're asking about. We don't necessarily have to balance the whole thing, but we can go ahead and do that just as practice. So again, in these types of problems, we're going to set this as a coefficient of 1 initially. We would call this our most complex species because it has the most atoms in it. So if we have 2 carbons over here, we need to put a coefficient of 2 in front of CO2 to balance carbon. And then this reactant has a total of 6 hydrogens, is written in this way to sort of indicate the connectivity, but it's a total of 6 hydrogen atoms. So we need to have 6 hydrogen atoms on the product side, giving a 3 there. And then the only thing that's left is to balance oxygen. So on the product side, we have 2 times 2 is 4 plus 3, we have 7 oxygens. On the reactant side, we have 1 here, which means we need 6 more, so 3 there. So that should be balanced. But again, for this problem, the important part is that we know the ratio of this reactant to this product, because those are the two that we're asked about in this problem. Now that we have a balanced equation, we can go ahead and start it. And again, we write out what we're looking for, which is going to be grams of water. And if we go through, we have to give our starting point, which is 8.04 moles of C2H5OH. Because we're already in moles, we don't have to do any conversions with this number. We're ready to go ahead and use mole ratios. So to find first how many moles of water forms, we're always going to go between moles of reactants and products because that's what the coefficients tell us. We want moles of H2O in the numerator and then moles of C2H5OH, ethanol, in the denominator. And we're going to again just use the mole ratios. 3 moles of water is going to form for every 1 mole. This doesn't have a coefficient. Remember, no coefficient implies that there's a coefficient of 1. So that gives us moles of water. But in this problem, we don't stop here. Before we were going just to moles and we stopped. Here we want to find grams of water. And so remember that if we want to go from moles to mass, we need grams of water in the numerator, moles in the denominator. And this ratio, grams per mole, is just going to be the molar mass of water. So we have to calculate that, which is not given here. The molar mass for water, we have 2 hydrogens, and then if we go to the periodic table, sorry, I didn't open that right away. All right, so our periodic table, we have to find the atomic masses of hydrogen and oxygen, add them together. So hydrogen is 1.008, oxygen is about exactly 16. And so we're going to have, for the molar mass of H2O, 2 times 1.008 grams per mole for the hydrogen, and then 1 times the atomic mass of oxygen, which is 16. And so if we want to do this, we would get something like 18.02, depending on how many decimals you round to. All right, so that's the molar mass of water. So we're going to use 18.02 here, grams of water per 1 mole. And then multiplying that out, which I didn't do, so give me a second here. We get 434, just 435, rounding it correctly, grams of water. All right, so 3 significant digits, since that's what our given information had. And so that's going to be what we get for this one, which is a mole to mass. So there's just one additional step, which is using molar mass to convert from moles back into mass of that particular substance. All right, and then the last major variation we had on sort of typical stoichiometry problems is this one here. So here we're combusting 10.6 grams of C4H10, which is butane, and we want to know how many grams of CO2 will that yield. Assume 100% yield. That basically means we're assuming we're going to form all of the CO2 that is possible to form. So in this problem here, we have grams of one substance. We're calculating grams of another. So this would be classified as a mass-to-mass stoichiometry problem, if we're trying to, again, categorize things in these ways. But once again, the key points are we need a balance equation first, and then from there we're going to figure out what we're looking for and use the given information to help us get there. All right, so the balance equation, this is again combustion. We should be familiar by now with what a combustion equation is. It's going to be whatever we're burning, whatever we're combusting, plus oxygen is the other reactant. And then we're going to yield CO2 and water. The important part again is in this problem we just have C4H10 and CO2 are the 2 substances we're considering, so we need to make sure we have the ratio of those correct. C4H10 has 4 carbons, CO2 has, so we need to have 4 of those to balance carbon, and then we have 10 hydrogens, meaning we need 5 waters, and then 8 plus 5 is 13 oxygens on the product side, so that means this has to be 13 over 2 to balance oxygen. If you don't like fractional coefficients, we can multiply this whole thing by 2, and we get 2 C4H10 plus 13 over 2 O2. Sorry, just 13 now. I got rid of the 2 by multiplying. So we're going to multiply this whole thing by 2, so we get rid of this fraction, and we get 8 CO2 and 10 water. So this would be the form that's balanced without fractions. It's not necessarily that important that you do that, so we could have left it like this. The important part is that the ratio of C4H10 to CO2 is 1 to 4 or 2 to 8 if we write it this way. So it doesn't really matter how we balance this, and as long as it is balanced, whether there's fractions or not, it's not going to affect how you do the problem. But let's go ahead and start it then. So what we're looking for is grams of CO2, so that's what we want to write out, and we're going to basically do conversions until we get there. In this case, we're starting with 10.6 grams of C4H10. In this problem, because we're starting with an amount that's not in moles, we have to do a conversion first before we can use coefficients from the balance equation. So if we start with grams, we have to convert to moles first, so we want moles of C4H10, and then we want grams on the bottom. And so in this case, we're going to basically divide by the molar mass. So 1 mole is how many grams. We have to find the molar mass of C4H10. It wasn't given to us here, but if we calculate that real fast, which I'm not going to go over in detail, the molar mass of C4H10 is about 58.12. So that's the mass we're going to use in the denominator. So this allows us to convert grams into moles. Once we have moles of one substance, we can convert to moles of the other substance by using the coefficients. So again, depending on which form of the balanced equation you use, either the top one or the bottom one, you're going to have different numbers with the same ratio. So we want to convert into moles of CO2, since that's what we're trying to find, and we want that relative to C4H10. So if we use the bottom form of the equation, which doesn't have fractional coefficients, we would get 8 moles of CO2 with a coefficient of 8, per 2 moles of C4H10, or we could have had 4 over 1. Mathematically, we'll recognize those are equivalent, 8 over 2 or 4 over 1. All right, so moles of C4H10, but then we don't stop yet because we want to find grams of CO2. So once again, we have to go to a second line in this case and use the molar mass. So we want grams of CO2 per mole. That will allow moles of CO2 to cancel, and then we're going to use the molar mass. So the molar mass of CO2, carbon plus 2 oxygens, is 44.02 grams per mole. All right, so this was a typical mass-to-mass stoichiometry problem where we started with the mass of one substance and we found the mass of another. And when we work this out mathematically, assuming I didn't make any mistakes, what I got was 32.1 grams of CO2. Keep in mind, for most of the problems that I'm doing here, a lot of the numerical inputs were variables, so you might have had different numbers in these problems. If you had the exact same one, it would likely have still been different numbers. But nonetheless, the approach for doing the problem is exactly the same, no matter what the numbers are. All right, so that's going to be how we do this one, mass to mass, starting with mass of one substance going to mass of another. All right, so that takes us through sort of the basic problem types in stoichiometry. Now with that, though, there's a few different things that we can sort of add into this. So in this problem here, we have 3.75 grams of calcium carbonate, CaCO3, reacting with excess hydrochloric acid, and then we're forming 1.37 grams of CO2. So here we're telling you how much of the product we produce. We want to know what is the percent yield of CO2. So in this problem, it's going to also be a mass-to-mass problem, but now we're finding percent yield. So recall that percent yield is the actual yield divided by theoretical yield multiplied by 100. So when you do a chemical reaction, you don't often get the exact amount of product that you expect. So the amount of product that you would calculate as being possible using stoichiometry is your theoretical yield. This is the part that's typically calculated, actual yield, and then we multiply that by 100 to get percent yield. So in this problem, the actual yield is given to us. This number here, 1.37 grams, is actual yield. So and we have to calculate the theoretical yield from stoichiometry. All right, so this is typically how percent yield problems work. We give you the actual yield of one of the products. You calculate the theoretical yield using stoichiometry, and then the ratio of those two will allow you to find the percent yield after multiplying by 100. The first thing we need to do in this problem is make sure that our equation is balanced. Again, the important part is that calcium carbonate and CO2, that we get those ratios correct. But let's go ahead and balance this equation. This looks a little weird, but it actually is just an acid-base equation. We learned about acid-base chemistry at the very end before spring break, and then that topic will be covered in the next homework assignment, which starts yesterday and is due in a week. All right, so those are the reactions and products. We can balance these out. It's not obvious in this case what our most complicated species is, but this one has the most atoms in it. So let's set that to 1. 1 carbon means we need 1 CO2. 3 oxygens mean we're going to form 3 waters. And then to make sure everything remains balanced, let's see, we have... what did I do wrong? Something wrong here. Let me try that again. All right, so calcium carbonate plus HCl, CO2, and water. Okay. 1 carbon, so we're going to make 1 CO2. The other element that appears only once, let's see, that's going to be calcium. So if we have one of those, we want one of those. We have 2 chlorides, so we're going to have I'm on the struggle bus right now. All right, I'm done spazzing out so we can balance this. That's my mistake, my fault. All right, so let's go through this. 1 carbon, so we're going to put 1 CO2. And then we have 1 calcium, so we're going to put 1 calcium chloride. And now if we look at what we have left, we need to make sure that chlorine is balanced. So we have 2 chlorines in this product, which means we have to have 2 HCl's. And then if we look at the rest that we haven't considered yet, which is oxygen, we have 3 oxygens over here. We have 2 plus 1, which is 3. Hydrogen, we have 2 and 2. So those are the only coefficient we need. We just need a coefficient of 2 in front of HCl. And end up being a little bit easier than it looked like. But again, the important part is that we have this ratio, 1:1 for calcium carbonate and CO2, which are the 2 things we're told about or asked about in this problem. So what we need to do is calculate the theoretical yield, basically the mass of CO2 that could form. So this is going to be another mass-to-mass stoichiometry problem. And so what we're going to do is when we're looking for grams of CO2, this is going to be our theoretical yield whenever we calculate it from stoichiometry. We're using 3.75 grams of calcium carbonate. And so once again, the first step is going to be to convert grams into moles using the molar mass. I don't have that number available right off the top of my head, but if we calculate that for calcium carbonate, we get 100.09. Hope I did that right. That sounds about right. Grams of calcium carbonate per mole. So this is the molar mass of calcium carbonate. We're going to divide by that to convert grams into moles. Once we have moles of this substance, we can find the moles of CO2 that would theoretically form. And the ratio is going to be, we just have a coefficient of 1 for CO2 and a coefficient of 1 for calcium carbonate. So it's just a 1:1 mole ratio, so the same number of moles of each. And then we want to find grams of CO2. We're again going to use its molar mass, which we used last time was 44.02 grams in 1 mole. All right, so a typical mass-to-mass conversion to be able to figure out how many grams of CO2 could theoretically form. And so the number that we get for that, which should be larger than our actual yield, because percent yield is never going to be more than 100%. Let's see what we get. All right, so what I got was 1.65 grams of CO2. Now, once again, that's our theoretical yield, which is then going to go back up here to calculate percent yield. I'll write it out again because we were running out of room up there. So the percent yield, which is what the final answer of this problem is going to be the actual yield, which was given to us as 1.37 grams, divided by the theoretical yield, which we just calculated as 1.65 grams, and then multiplied by 100 to get it into a percentage. Okay, so what we get for that should be somewhere around 83.1%. All right, so when you're calculating percent yield, it's typically going to just be one extra step. You're going to use stoichiometry to calculate a theoretical yield, and then you're going to divide the two. There's no way to really calculate the actual yield unless we gave you the percent yield. So I don't have a problem like this, but a variation on this problem would have been, we could have given you the percent yield as a given, you would have still calculated the theoretical yield using stoichiometry, and then we're going to solve for this number here. But there's only going to be one variable in these problems, and more typically as it is here, you're going to be just solving for percent yield, where the actual yield will be one of the given numbers in the problem. All right, so that was sort of just taking it one step further with using the definition of percent yield and calculating it. All right, then the next two problems we're going to do are going to deal with the concept of limiting reactant. So all the problems that we've done so far, we've only had to deal with an amount of one reactant, and we were in some cases explicitly told that there was, everything else was in excess. So let's go quickly through these problems here to see what I'm talking about. So in this problem, we just gave you the moles of one reactant, and you had to calculate the moles of another reactant and moles of product. In the second problem we did, we gave you moles of one reactant. We told you explicitly that the O2 was in excess here, so we only had to worry about the amount of one reactant. Third problem we just gave you the mass of the reactant. We didn't tell you anything about the amount of O2, so you assume that there was excess O2. And then similarly down here, calcium carbonate reacts with excess hydrochloric acid. So in all of the previous problems, we either only just gave you the amount of one reactant, or we explicitly told you that the other reactant was excess. And so in that case, you assume that you're going to just start with that amount of substance and do your calculations like we did. But in some cases, what we're going to have is we're going to give you the amounts of 2 reactants or more than 2 reactants if we're being really unfriendly, and then you have to figure out which is the limiting reactant. So anytime you know the amounts of 2 or more reactants, whether it's moles, grams, or any other quantity, you have to determine which of those is the limiting reactant before you can do any calculations. So this first problem here is a true-false problem, and 50% of you got it right. So whenever there's a success rate of 50% on a true-false question, that's a little bit alarming. It basically means that we would have done just as well by guessing. So let's go through this. This problem just deals with the definition of a limiting reactant, or how you determine what it is. So given the equation 3A plus B goes to C plus D, you react 1 mole of A with 3 moles of B. True or false? A is limiting reactant because you have fewer moles of A than B. Now this is a common trap that people fall into. To find what the limiting reactant is, you cannot just know how many moles there are. That's part of it, but just knowing the number of moles of substances does not tell you what the limiting reactant is. So A might be the limiting reactant, but it's not because you have fewer moles. That's never the reason why something's a limiting reactant. So the way that we can actually figure out what the limiting reactant is using stoichiometric ratios. So remember that the definition of stoichiometric ratio is moles of substance divided by the coefficient. So for reactant A here, we have 1 mole. And we're going to divide that by the coefficient, which is 3. So the stoichiometric ratio for A is 1 over 3, or 0.33, however you want to calculate that. The stoichiometric ratio for B is going to be the moles of B. We have 3 moles of B, and then its coefficient is 1, so it's going to be 3. So this number here tells us, because this is smaller, that A is limiting reactant. So that is true. That part of the statement is true. A is limiting reactant, but it's not because you have fewer moles of A than B. Okay? We could have had a situation like this where, let's say we had instead 2 moles of A and 1 mole of, 1 mole of B. That will still work, yeah. So let's say instead we had 2 moles of A and 1 mole of B. The stoichiometric ratio for A would this time be 2 over 3. Number of moles, I should just leave the units out, a little bit confusing to write those in. So remember that the stoichiometric ratio is moles of substance that you have divided by the coefficient, which is still 3 for A, so that would be 2/3. And the stoichiometric ratio for B would still be 1 mole of B divided by the coefficient of 1, which is 1. So in this case, A is still the limiting reactant because its stoichiometric ratio is smaller, but we have more moles of A. So the key part of this question is that A is limiting reactant, but it's not because you have fewer moles. It's because the stoichiometric ratio is smaller. So this one would be false, because even though it's true that A is limiting reactant, the reason why is wrong. Okay, so finding the limiting reactant, this sort of gives us a review how to do that. There's a few different ways of approaching it, but the way that I taught in class and that I like to use is finding these stoichiometric ratios. Moles of substance divided by coefficient, whichever of those is smaller, identifies the limiting reactant. But the one that has fewer number of moles is not necessarily going to be the limiting reactant. So that was the key part of this question. So now let's put that into practice with this problem here. So we have calcium reacting with sulfur to form calcium sulfide. Now there's 2 ways of writing the balanced equation. The way that most of you probably did it at this stage in the course was just to say calcium is Ca, sulfur is S, and then we have to form our product. Now calcium sulfide, remember we have to figure out the formula of the product. So if we go back to the periodic table here, it's an ionic compound, so we need to figure out the charges of the ions. So calcium is in here, it's in group 2 of the periodic table, so it's going to be a 2 plus cation. Sulfur is in group 6, it's going to form a 2 minus anion. And so when we want to find the formula of calcium sulfide, we have calcium 2 plus S2 minus, sorry, 2 minus was the charge. That means the formula of calcium sulfide is just CaS, one of each to balance the charges, okay? So that means the reaction could simply be written as calcium plus sulfur going to CaS. In reality, elemental sulfur exists as S8. We'll talk about that in chapter 7. So another way to write the balanced equation, which is actually technically more correct, would be this, and then if we want to balance this, we have to put an 8 there and an 8 there. So if we want to use whole numbers. It actually doesn't matter in this problem which form of the equation you use, you'll get the same answer either way. So don't worry if you used a different form, which form of the equation you use. As long as it's balanced, it's going to be fine. So calcium plus sulfur going to calcium sulfide, or the more correct one here. I will use this top one just because I'm assuming that's how most of you did it, and it's fine, as I said, to do it that way for this problem. Okay, but in this problem here, we're looking for theoretical yield of the product if we have 3.34 grams of calcium and 3.75 grams of sulfur. So this is a classic situation now where we have amounts of both reactants. We know how much calcium we have, we know how much sulfur we have, and so we need to go through and figure out first which is the limiting reactant. So before we can figure out how much of our product forms, we have to determine which of those, calcium or sulfur, is the limiting reactant. So I'm going to get rid of this just to get it out of the way and give myself some more room. And now let's go ahead and use this top equation to approach the problem. Okay, so to find this, what we're going to do is we're going to first find moles of each reactant. So moles of calcium, we have 3.34 grams. And then we're going to use the atomic mass of calcium. So the atomic mass of calcium is 40.08. If it's just a single element, you don't need to calculate a molar mass. You just use the atomic mass from the periodic table, which is 40.08. All right, and so what we get for moles of calcium, hang on a second, 3.34. All right, so we get 0.0833. And then the stoichiometric ratio for calcium is going to be that number divided by its coefficient. In this form of the equation that we're using, the coefficient is 1, so the stoichiometric ratio is just the same number. But again, to find the limiting reactant, you have to divide by the coefficient. You can't just use the number of moles directly. And then we're going to do the same thing for sulfur, the other reactant. So we have 3.75 grams of sulfur. And the atomic mass of sulfur, if we're just using the form S, 1 mole of sulfur is going to have a mass of 32.07 grams. So we get a number that's slightly larger, 0.117. And that means the stoichiometric ratio for sulfur is going to be that number divided by its coefficient, which is also 1. And so we get 0.117. All right, so then the number of which of these is smaller? This number here is smaller, so that means calcium is our limiting reactant. Whichever stoichiometric ratio is smaller. In this case, they both had the same coefficient, so it also works out that the one that has the smaller number of moles would be limiting, but that's not generally true. You have to divide by the coefficient to make sure that you get the proper stoichiometric ratio, and then use that to figure out what your limiting reactant is. So that's going to be calcium, which means we're going to start all of our calculations with calcium. Now, what are we looking for here? We're looking for theoretical yield of calcium sulfide, so how much of the product calcium sulfide can form. And so now we're going to just set up a mass-to-mass stoichiometry problem. Grams of calcium sulfide that can form from 3.34 grams of calcium, which is our limiting reactant. Now, we already calculated moles of calcium, so we can actually start with this number and save ourselves a step in this last calculation here. So we have 0.0833 moles of calcium. We already got that number, so we don't have to do it again. And now we can use mole ratio. So we have 1 mole of calcium sulfide forming for every 1 mole of calcium that reacts. And then we just have to use, to find grams of calcium sulfide, we have to use its molar mass, which is just the sum of the two atomic masses. So that's going to be something like 72.15. So we have 72.15 grams of calcium sulfide in 1 mole. And so that's going to be our last step to figure out how many grams of that product we form. And so what we get is 6.01 grams. So this is the maximum amount of calcium sulfide we can form. Now, if we'd started the calculation with sulfur, we would have gotten a number that's larger than this, which is not correct because sulfur is our excess reactant. We have to always start with the limiting reactant. which in this case is calcium. All right, so that's another sort of thing that can come up in these types of problems is limiting reactant. All right, the last couple problems I want to do, this one is a sort of a pictorial problem that also deals with the concept of limiting reactants. I think the difficulty in this one is to figure out what to do with the picture. So the circles below depict the reaction of AB2 and B2. So if it's AB2 and B2, that would mean that A should be represented by the black spheres. So we have A, B2, and then B is going to be the orange ones, or brown, or whatever you want to call that color. So we have B2, and then we have A, B2. Okay, so that's the colors that are represented. And in this problem, we don't want to actually use these pictures too much to read into the numbers here. What we want to use the pictures for is to find a balanced equation. So these are reactants, and this is the products plus excess reactants. So in this case, there are excess reactants present because we still have some B2 left over. But the point of all this is we want to figure out what is the chemical equation here. So we see that the only new product that we're forming on this side is AB3, right? So we start with AB2 and B2, and then we're forming AB3, 1 atom of A, 3 atoms of B, so that's our product. So basically the chemical equation now is going to be AB2 plus B2 forming AB3 as the only product. So on the product side, that's the only new thing we have. And then we just have to go ahead and balance this. So this one's a little bit tricky to balance, but what we're going to end up doing, I believe, is we can put a 1/2 here, and then if we want to get rid of fractions, so this 1/2 would balance it because we have 1A on each side, we have 3B, so that's going to be 2 plus 1, and then we can multiply the whole thing by 2 to get a balanced equation that's just 2AB2 plus B2 goes to 2AB3. So this is our balanced equation, and then for the rest of the problem, we're just going to use the numbers that we give us. If 5 moles of AB2 reacts with 3 moles of B2, how many moles of B2, if any, would remain unreacted? So the first thing we need to do in this is figure out what the limiting reactant is. So in this problem, we have AB2. If we want to find its stoichiometric ratio as we did before, we have 5 moles. That's what we're given in the problem, 5 moles of AB2, and its coefficient is going to be 2. And then the stoichiometric ratio for B2 is going to be, we have 3 moles of B2, and then its coefficient is a 1. So that means that AB2 is the limiting reactant in this problem, meaning that there will be some B2 left over. So we're trying to find how many moles of B2 remain unreacted. There will be some because B2 is the limiting reactant. So what we want to find then is the moles of B2 that are consumed, that react in this equation, are going to be, we have 5 moles of limiting reactant, AB2. So if we want to find out how many B2 is reacting, we have to start with moles of limiting reactant. And then the ratio of B2 to AB2, we're going to react 1 mole of B2 for every 2 moles of AB2. So that means we're going to react 2.5 moles of B2. And that means the excess B2 we have 3 moles of B2 to start. We're reacting 2.5 moles, so we have 0.5 moles left over. All right, so that would be the answer in this question. So I think the hard part about this one was not the problem itself, although it is a new type of problem we haven't seen yet. But the hard part is, what do we do with these pictures? The pictures were just used to figure out what is the product of this reaction. AB2 plus B2, the new product that forms is AB3. From there, we can scrap the pictures. We can use that information to write an equation, balance the equation, and then go through and do the stoichiometry. The difference in this problem is we're trying to figure out how many moles of excess B2 there is. So identifying first that AB2 is limiting reactant, B2 is in excess, and then to figure out how much excess reactant is left, you figure out how much of that reacts using the stoichiometry, the mole ratios, and then subtraction gives you how much is left over. So a lot of steps in this problem, none of them particularly difficult mathematically, but we had to again figure out what to do with the pictures. All right, last problem I want to go through is one that we didn't exactly cover in class. There are two ways to do it, but at this point probably only one of those two ways is something that we would have really been comfortable with. So the Claus reaction shown below is, the Claus reactions I should say, are used to generate sulfur from hydrogen sulfide. So this is sort of a two-step reaction. So what you'll notice here is that we're going to take hydrogen sulfide, we're going to oxidize it to make SO2 and water, and then in the second step we're going to use the SO2 that we form, react it with more hydrogen sulfide, and then we're going to have and then we're going to form sulfur and more water as our products. So there are two ways of approaching this problem. One way would be, and we're going to learn how to do this in chapter 7, so I'm not going to cover it now, it's not something we have yet, would be to combine these two equations into one. So basically SO2 is formed as a product in the first reaction, it's consumed in the second reaction. It would be possible then to combine these, to add these two equations together to get one chemical equation that describes the overall transformation. But that's something we're not going to be able to do just yet, so I'm not going to cover it here. What we can instead do is just do sort of two stoichiometry problems. So we're starting with 10 grams of O2, that's our reactant in the first equation, the first step here. We want to know how much sulfur is formed. Sulfur is not formed until the second equation. So the way we're going to do this is we're going to first figure out how much SO2 formed, because as I said, SO2 is formed in the first equation, first reaction, and then it reacts in the second reaction. So what we're going to do is figure out how much SO2 forms from 10 grams of O2, and then we're going to figure out if we have that much SO2, how much sulfur forms when that reacts in the second step. So this is going to basically be two mass-to-mass stoichiometry problems. So step one, let's figure out how much SO2 forms in the first step. If we have 10 grams of O2, it's going to be a mass-to-mass conversion to figure out how many grams of oxygen form. Now, technically speaking, we could stop at moles of SO2 if we wanted to. So let me basically do this way first since I already started, and then I'll show you how we don't even really need to do the full mass-to-mass conversion. So grams of SO2 we can find. So we're going to find moles of O2 using its molar mass. And then we're going to use the coefficients from the first equation to figure out how much SO2 forms. So we have 2 moles of SO2 forming for every 3 moles of O2 that reacts. And then if we want to go all the way through and find the mass of SO2 that forms, what we would get is its molar mass is about 64. So we have 64.07 grams of SO2 for every mole. And so the number that we get for the mass of SO2 that forms is 13.3 grams. Okay, so that's how much SO2 forms, and then in the second step we're going to figure out how much sulfur is formed here, S. And so in the second step we're going to find mass of sulfur, and again it's going to be another mass-to-mass problem. We have this many grams of SO2 that formed in the first step. When they react, how much sulfur is formed. So we have 13.3 grams of SO2. So we have 13.3 grams of SO2. We're going to convert that to moles using its molar mass. Now what you'll notice here is that this first step of the second problem, or the second calculation we're doing, we're basically just undoing the last step in the first one. So probably the smarter way to do this problem would be to just stop here at moles and then use the moles of SO2 in the second calculation. That would save us a little bit of time. I feel like it's more typical or more intuitive for students to go mass to mass when in doubt. So that's why I did it this way. But either way it works, but we could have saved ourselves a little bit of time by just using moles of SO2 directly. But once we have moles of SO2, we can then figure out how many moles of sulfur forms from that. So it's going to be 3 moles of sulfur forming, there's a coefficient of 3, for every 1 mole of SO2 in the second step. And then to find grams of sulfur, we're going to use the atomic mass of sulfur, which is 32.07. And so when we work that out, what we get is about 20.0 grams. All right, and so that number matches choice D, so that's what we would pick here in this multiple choice question. So in a two-step stoichiometry problem like this, really the way that's going to make the most sense at this point would be to do two separate calculations. Figure out how much SO2 forms, and then that's going to be the species that's consumed in the second reaction, so then start with that amount to figure out how much of the sulfur forms. All right, so that takes us to the end. All different kinds of stoichiometry problems covered in this review. If you have any additional questions on this, please get in contact with me. Best wishes as you start your online classes this week, and I'll see you online hopefully.